All right, cool. Audio check. All right, sounds good. All right, so yeah, again, I'm Christopher. This is Xiling, and we wanted to go over how to port, your SoC to using the MCU Caliptra Subsystem SDK. So we'll talk a little bit about this and about what MCU is and what it does and its role in the system. Talk a little bit about actually building it and how to use our SDK over the next few minutes. So just as a quick overview, I know we've seen a lot of talks on Caliptra, but it's always good to have a nice reminder when we're talking about building something with it, exactly what the responsibilities of Caliptra Core versus the MCU are. So Caliptra Core is this block. The details don't matter a ton, but it's the core cryptographic and identity services, right? This is a frozen block. It's RTL given to you, ROM given to you, firmware given to you, can't really change it. Like it is meant to be used as is, so it's not really customizable. And then zooming out a little bit, so that's now in the upper left corner there. When you look at the entire subsystem now, there's a bunch of other components that come in. So now you're building your security subsystem using that Caliptra core as that fundamental identity and crypto block, right? And now I need to bring in the rest of my SoC into it, right? So MCU is down in the bottom right there. That's another RISC-V processor. And then the rest of your SoC components will be there. And then there's all the other pieces we've had talks on today, lifecycle controller, views controller, things like that as part of it. But when we talk about the subsystem, it's all of this, and the MCU SDK kind of covers interacting with all those pieces, right? So it's really about the software running on that MCU core in the bottom right, but kind of managing all these pieces and how they work with Caliptra. So that's what I said there. In general, when we say MCU, manufacturer control unit, it's really just a second RISC-V core that's companion to Caliptra. The firmware is actually going to be built by the SoC itself, so it's customized firmware. It's not mandatory by the consortium, so you can do whatever you want in it theoretically, but we provide our SDK to kind of give you some building blocks to hopefully do common things that you'll be wanting to do anyways, like working with Caliptra, working with the fuse controller, things like that. Yeah, and so that also means since it is so customizable, everything about it is going to be specific to your needs. We can't really bless an official ROM or an official firmware, but we can give you an SDK and let you work with that. So the working group has developed our Rust firmware SDK. It's all written in Rust, just like the rest of Caliptra. We think Rust is kind of the future for building firmware in general. I'm happy to go into that at great length, but I'll skip over that right now. But feel free to talk to me about Rust. I'm generally a fan. There's a bunch of common ROM routines that you can use to build with it that help you do things like manage the fuse controller, lifecycle controller, get the secure boot, the recovery boot going, things like that. And then as well as a runtime based on TalkOS, which we've discussed a little bit today. And then there's also some extra tools in there to help you manage your fuse map. So you have some like very general fuse like partitions that are set up by the hardware, but you kind of want to divvy those up in software, maybe at a more fine-grained level. So we have some tools for things like that. And then we support, like, if you want to either fork our code and then just work off of a fork, or we do support a workflow where you can depend on us as a Rust cargo dependency, and then that way it's a little bit easier to keep track of, and then you don't have to merge upstream changes with your fork necessarily. But we support either development flow, I think. So however you want to work with us is how you want to. As far as how the stack kind of goes, this is getting a little bit into the runtime architecture now. It's split a little bit so that the left-hand side is kind of the user space, and the bottom side is kind of the ROM and the kernel space. So in general, the way Talk is structured, it's a user space, kernel space separation. So you have your applications, like say your SPDM or your PLDM, running in user space as an application, and then they use a bunch of services that are provided by the kernel. So it's kind of like a microkernel architecture. Everything you do is a syscall into the kernel anytime you want to do things like send an MCTP packet, or maybe read from the fuse controller or something like that. Those are all syscalls you make in, and then the kernel will handle all the hardware stuff, like actually messing with your I3C controller, or messing with if you're messing with the fuse controller, stuff like that. Anytime you touch a hardware CSR, the kernel should be doing that. The software is caring more about higher level flows. So if you have, like, I want to manage all these firmware updates in progress, it cares about that. Kernel cares about hardware. And that's just kind of showing this stack. And then the kernel is, of course, customizable. You can add your own hardware drivers into there as well. TalkOS, to kind of talk a little bit more about that, we've mentioned it a few times in several talks today, but haven't really dug into what it is. It's an academic project that's really meant to be a very customizable, secure RTOS, so real-time operating system. So it provides some real-time guarantees about performance. And it's very Rust-like. So it's written in Rust, so it works quite well with Rust code, and it takes a lot of those Rust isms and kind of embodies that in the way that you manage memory with it. You have to share memory with the kernel, for instance, and so it kind of borrows it in the same way that Rust does. Yeah, the kernel is custom though, so like it gives you more like the pieces of a kernel that you then build into your system with a board file and a chip file. And things like that. Our documentation goes into some details on this, as does Talk's documentation. And I already discussed kind of the user kernel separation. Since our RISC-V processor does support physical memory protection, so the enhanced physical memory protection spec is used to protect things. So not only should your user application not be messing with hardware registers, it can't by default. Like, we actually lock it out so it doesn't even have access. So capsules, this is really just the general way that Talk refers to kernel modules. So whenever you hear kernel modules in some systems, it's a Talk capsule. I won't go into all these details here so that we can get moving, but in general, there's only 5 syscalls that are supported, and then Talk services those by passing them to a capsule, which then we'll probably call like a hardware driver or something like that. So. In general, whenever you're looking at Caliptra, the MCU, in particular the MCU SDK, it's this repository. So this is where all the main development happens. The instructions are kind of to get started are install Rust, of course. And then everything is xtask. So xtask is a pattern in a lot of Rust projects. But if you run cargo xtask in there, you'll see everything that you can do. There's no shell scripts, there's no make files, there's no build system, anything like that. It's all built into this xtask command. So it makes it a lot easier to kind of get started. You can just see everything you can do. You can build the ROM, you can build, run the emulator, like generate, registers, things like that. All can be done just with this xtask one. And if you just run, say cargo xtask runtime, we'll run the runtime in the emulator. You should see everything boot up. It kind of should just work. And then hopefully that gives you a good platform for building things off of that yourself. But we try to make it as straightforward as possible to get started. I think Xiling is going to take it from here.
All right, thank you, Chris. Let's take a closer look how to use our SDK and how to port this SDK to a different platform. We can start from like in-tree or out-of-tree platform directory. In our current MCU software repo, we have the porting to the emulator platform and FPGA platform. So that's a good reference point to start your platform porting. You can add the crate for the config ROM runtime, similar to the way we have done. And in the platform config, the memory map straps and RTL constants can be defined. And the fuse map can be generated through our fuse map generator. Now let's take a look about the ROM. So ROM is usually very hardware-specific, integrator-specific. You should own your ROM entry point. We prefer the ROM to be implemented in Rust. Inside the ROM, it initialized all the SoC hardware like PLLs, and then jumping to the common ROM, which is part of our current reference SDK that can boot the Caliptra and MCU firmware. Coming to the runtime, the board file, board.rs, for the emulator and FPGA are good examples as the starting point. And then this board file is highly customizable. We can create the Talk kernel, initialize all those kernels and load capsules that's relevant to your hardware, to your platform. And then the upper level is to load the applications, and then the kernel loop starts. So this is the full runtime flow. Coming to the user space, so thanks to this Tux microkernel architecture, the user space application is fully isolated from the kernel, and then we can write our own apps that perform the logic that required by your platform. In the current MCU software repo, we provide a reference implementation for the application. We have a user app and example app. So the PLDM and SPDM protocols are implemented as the async library. We have this talk in the morning. And then the application can exercise those flows like attestation, firmware update, streaming boot through the user space. We also introduced Embassy Executor, which is interoperable with Talk to exercise those, to support those async workflow. This application can only access those hardware through the system calls, as we mentioned before. This is the mandatory requirement by the Talk OS. So now we are looking forward to any contribution to the MCU SDK. Feel free to open any issues, create PRs, and we are more than happy to review and to discuss any open questions or any design or initiatives. We will have our SDK available for 2.1 very soon. Currently, we have 2.0, right? Our SDK.
I wouldn't say it's quite. I wouldn't say it's quite available yet, but it's kind of ready for people to start using it, but we haven't tagged an official release yet. And then also the releases aren't quite as official as Caliptra ROM, right? Because it's not like there's nothing frozen in this, so it's all meant to be used by an integrator. So there's not an official it's 1.0 necessarily, but we'll have a more final release, I think, in the coming weeks. For 2.0, and then 2.1 will follow a little bit later. But
this is very active working stream.
Yeah. We're working very hard on it. So.
Yeah, thank you.
Yeah, thanks. We have a few minutes. We've got a few minutes for questions, I think. So.
Yeah. Any questions? Work your way to the mics.
Which version of SPDM do you support at this time?
I believe for SPDM, for our initial release, we're doing 1.3, and then we're working right now on the 1.4 post-quantum support for MLChem and MLDSA. So, but right now we have it working pretty well for 1.3. It runs the full libSPDM validator suite against our FPGA and everything. So.
Okay, thanks.
Thanks, Chris. I'll ask the same question I asked the OpenPROC guys.
Yeah.
Did you choose between the Talk OS and the Hubris OS?
So we started development on this a little bit earlier, right? I think a year and a half ago is when we really got going, and Hubris wasn't quite ready, I think, for us to use. And there's also a little bit of concerns. I really like Hubris a lot, but it is controlled by another company. It's open source, whereas Talk is controlled by an academic project. And so there's always a little bit of concern that a commercial company, are they going to cooperate with us if we have changes and whatnot? Whereas Talk OS generally does, but they do want it more focused on kind of academic research as well. So there's tension either way. Hubris is definitely very interesting, and if I started work on it today, I would strongly consider Hubris. But I think when we started a year and a half ago, the calculus was a little bit different. But no, Hubris is great. I'm very interested in it moving forward. Yeah.
And as a direct follow-up to that, do you have any recommendations for avoiding duplication of effort across the ecosystem with OpenPROC being Hubris and this being?
Yeah, I mean, I think there's a lot of code reuse amongst all of us, right? So we're using OpenTitan blocks of hardware, and then OpenPROC is using some of our SPDM and PLDM implementations, and they said they would contribute those back. Happy to chat with them, to keep that going forward. They're kind of separate use cases in a lot of ways, but I think they're also complementary in some. So I don't think there's any problems like that. We're sharing a lot of code already. So.
Yeah. Can you talk about the memory footprint for the SDK?
I'm sorry, what
memory footprint for the SDK?
Oh, memory footprint. Everyone always wants to know about this. I think we said we're trying very hard to target a 384 kilobyte SRAM for MCU in particular. Hopefully we'll keep within that. It's tough. PQC is the post-quantum stuff, the cert chains get very large, and it gets very challenging to stay within that budget. That's what we're targeting. I don't want to make a promise at this point though. Like, we're doing
And
what
can we disable certain features like
Yes.
MCTP?
You can disable so this is the beauty of it being fully customizable is you can do whatever you want. Like ultimately the SoC, whoever's writing it, is responsible for that firmware. So if there are pieces you want or pieces you don't want, you decide you don't want MLDSA to save space.
I mean, is
for
there some
instance.
flag-based system to disable it, or we have to just remove those pieces? Work on it?
Right now you have to remove those pieces. We can add flags to disable certain pieces. The apps that actually do like the PLDM and SPDM are all custom at the moment. It's more, we have libraries that you would use, so it would be more that you just wouldn't pull those pieces in.
Yeah, thank you.
Yeah. We have time for that, yeah.
Yeah, how does the support model is going to look like?
Support model, like what do you want out of support?
Like once you adopt it, right? Like folks are used to adopting RAM, FMC runtime, leaving it as is, shipping it, but this is more dynamic.
Yeah, I mean, this is more dynamic, right? So like ultimately, again, like the final responsibility is going to be up to the integrator because at the end of the day, they're the ones that have to pass FIPS certification, right? They're the ones that have to like live with themselves at this, right? Like I the SDK author, I'm happy to help, but ultimately it's not my job on the line, right, as the integrator, right? So like we're happy to help and we contribute to things like the CHIPS Alliance forums for like the CHIPS Alliance, like the weekly meetings and stuff like that for people to ask questions. But, like we do what we can, but it is kind of a best effort basis as there are very few of us and a lot of everyone else.
All right, thanks a lot, Chris. So we don't have much more time for any
Sorry.
other questions. If you can take more questions outside, but we have to prepare for the next talk.